Bonjour. Hello, everyone. I'm sorry if I have a bad French accent. My name is Dianing. I'm a software engineer, and I've been coding for more than 20 years. I've worked with many people in different cultures, different teams, and different organizations. I've worked in small projects. I've worked in medium-sized projects, as well as big, long projects that last for months. What I noticed from my experience is that some of the knowledge and lessons learned by any of the team members, junior, senior, whoever, can be very valuable, but they can get sometimes lost or forgotten. Sometimes we even miss the opportunity to learn the lessons in the first place. In this talk today, I'm going to talk about what have been preventing us from learning our lessons in the first place, and a lightweight technique to start collecting the lessons learned, as well as ways to benefit from them. Who ever wanted to become a rocket engineer? Anyone? Nice, that's great. Who ever wanted to become an astronaut? Ever? Oh, yes. For me, it was when I was 13 years old, until someone told me, no, you're a girl, you can't be an astronaut. Not a reason why I'm not an astronaut right now. But yeah, rocket engineering is a rather fascinating field. And we, as software engineers, did I say software engineer or rocket engineering? Okay, let me trace back again. Rocket engineering is a rather fascinating field. And we, as software engineers, or people who are in the software engineering world, can learn some things from it. This is a picture of Space Shuttle Challenger. It's the second space shuttle orbiter to fly into space. What's interesting about this space shuttle is that when it was built as a test article. It wasn't built for spaceflight. When NASA found that upgrading the original space shuttle would be much more expensive than upgrading Challenger, they changed their mind. Challenger was pushed into operations in the Space Shuttle program. Now, this may sound a bit familiar for some of us. I mean, how many times have you heard or even said, oh, this software prototype works pretty well. Let's just throw more features in and release it to production. Yeah? Well, I'm definitely guilty of saying that far too many times than I want to admit. Anyway, let's get back to Challenger. Challenger's first launch was in April 1983, which was 40 years ago. During its 3 years of operation, it was flown on 10 missions, spent more than 62 days in space, and completed around 1,000 orbits around the Earth, which was rather impressive, considering that it was originally built as a test article. However, on its 10th flight, things went awry. It was in January 1986. Challenger was scheduled to launch at 9:38 in the morning Eastern Time. The air temperature at the scheduled launch time was -3 degrees Celsius. Now, the air temperature is important to seal the fate of the space shuttle on that day. Challenger never took off at such a low temperature, so consultations were made to make decisions whether it was safe to launch. Engineers said, no, do not launch below 12 degrees Celsius, which was the previously lowest temperature of Challenger's launch. But at that time, there's this big pressure from the media, and there's high expectations from the public. They really wait for the launch of Challengers on that time. And they just watch the television. Some people even wait there. They want to see it. I mean, I don't know, maybe some of us was there as well. So after more consultations and inspections, the NASA managers decided to overrule the engineers' decision. They gave the launch the go-ahead. Challenger was cleared to launch at 11:38 a.m. Eastern Time, 2 hours after the originally planned scheduled time. It took off. The way it had taken off 9 times before. This is the 10th mission. However, this time, the pressurized burning gas leaked out of one of its solid rocket booster. It's quite high. Solid rocket booster is the white thing there. So there are 2 of them, solid rocket boosters, right and left. And the leakage was on the right rocket booster. Now, in normal circumstances, an O-ring will create a seal and contain the pressurized burning gas. However, the cold temperature in the booster joint prevented the O-ring to create a seal. The pressurized burning gas could not be contained. The faulty booster joint opened up, leading to a flame. It melted the securing struts, and then it led to the explosion of the external fuel tank. The external fuel tank is the dark orange or brownish thing, the big one there, between the 2 booster joints. And it's filled with fuel, really. You give fire to fuel, you know what happens. So after the explosion of this external fuel tank, the pressure waves and the aerodynamic forces destroyed the spacecraft. Challenger disintegrated 46,000 feet or 14 kilometers above the Atlantic Ocean, just off the Cape Canaveral, Florida, 73 seconds after it took off. Now, I'm not going to talk about why sometimes prototypes are released to production, nor am I going to talk about trying to draw a lesson from a failed O-rings into the software engineering world. But I would like to talk about the other reason of Challenger's accident. Failures in communication. After the Challenger accident, President Ronald Reagan created the Rogers Commission to investigate the accident. The commission criticized NASA's organizational structure and the decision-making processes that contributed to the accident. They found that test data since 1977, which is 6 years before Challenger's first launch, revealed a potentially catastrophic flaw in the solid rocket booster's O-rings. Neither NASA nor the solid rocket booster manufacturer addressed the issue. They just ignored them. On top of that, NASA managers disregarded engineers' warning about launching in cold temperature. They did not even report those technical concerns to their superiors. Rogers' Commission offered 9 recommendations. 2 of them are an overhaul of the shuttle management structure, start to embed astronauts in the management. I don't know if they like it, maybe they do. And the creation of shuttle safety panel. They also recommended an improvement in communication. In response, NASA created a new Office of Safety, Reliability, and Quality Assurance, headed by a NASA Associate Administrator, who reported directly to the NASA Administrator. Let's travel forward 17 years after Challenger's accident. This is a picture of Space Shuttle Columbia. It's the first space shuttle orbiter to fly in space, even before Challenger. Its first flight was in April 1981, 2 years before Challenger's first flight. Challenger's was in operations for 3 years, while Columbia was in operation for 22 years. It kind of tells the quality of software prototypes released to production compared to building software which is intentionally built for production, right? 3 years and 22 years? But anyway, I'm not going to talk about that. Let's get back to Columbia. In its 22 years of operations, it was flown on 28 missions. It spent more than 300 days in space, and it completed about 4,000 orbits around the Earth. Its last mission was in January 2003. It took off from the Space Kennedy Center, and when it took off, a large piece of foam insulating material broke free from the left bipod ramp. So the fuel tank is the big brown thing in the middle. So say this is the fuel tank, the external fuel tank, and this is the Columbia Space Shuttle. The space shuttle is attached to the fuel tank using bipods, two on the forward and one bipod forward and two bipod aft. And when Columbia took off on its last mission, the forward bipod, the left one actually, the left bipod ramp, had some foam insulation that just shed off. It broke free. It was flawed. And when the foam broke free, it hit the left wing. It's quite high. The leading edge of the left wing. And it created a hole more or less the size of my hand. It was a small hole, but not only the foam insulation made a hole, it also broke the protective carbon heat shielding panels. Columbia managed to fly into orbit successfully. It spent about 16 days in space until the mission was finished. The mission was finished in February 2003, and Columbia was coming back to Earth. However, the damaged left wing led to bigger unfortunate events. When Columbia was re-entering the Earth's atmosphere, the intense heat of hot gas penetrated into the interior of the wing through the little hole there. It's very little, but the hot gas could get in there. And it compromised the hydraulic system, leading to the control failure of the control surfaces. And with the loss of control, other areas of the Columbia Space Shuttle were exposed to the full entry heating and dynamic pressures. The heat and the pressure together destroyed Space Shuttle Columbia. Columbia disintegrated as it re-entered the atmosphere just over Texas and Louisiana. Now, this accident doesn't seem to have anything to do with the Challenger accident, right? Well, yes and no. Yes, because Challenger's accident was caused by the fault O-rings, while Columbia's accident was caused by the foam insulation material, shedding of the bipod ramp. But no, because both of the accidents were also caused by a failure in communication. More facts. The foam problem was well known and had caused shuttle damage on every prior shuttle flight. Immediately after the Columbia accident, NASA created the Columbia Accident Investigation Board to investigate the accident. Apart from the issue with the foam insulation, the investigation board also concluded that NASA had failed to learn many of the lessons from Challenger. The board believed that the cause of the institutional failure responsible for Challenger had not been fixed. 17 years apart. They said that the same flawed decision-making process that resulted in the Challenger accident was responsible for Columbia's destruction 17 years later. The investigation board made 29 recommendations this time, not only 9. And one of them was to establish an independent technical engineering authority that is responsible for technical requirements and all waivers to them. So what can we learn from this? How can they help us improve software development? Before we move on, I want to make sure that everyone's on the same page. I hope all of you agree that the main point so far is that failures in communication lead to failures to learn. So what can we do about it? Communications can feel natural, but it can also sometimes be hard. What makes it hard? In the case of the space shuttle accidents, communications were difficult because although the engineers voiced their concerns and opinions, many times, over many years, the managers chose not to listen to them. In other organizations, communication could be hard for other reasons. When Alan Mulally, CEO of Boeing Commercial Airplanes, moved to becoming the president and CEO of Ford Motor Company, he created a system to detect problems. He asked his managers to color code their reports: green for good, yellow for caution, and red for problems. At his first few meetings, all of the managers coded their reports green, which is great, right? Well, that's frustrated Mulally. He reminded everyone that they have lost several $1 billion in the previous year. So he just asked straight away, "Isn't anything not going well?" Then one yellow report was made with about a serious product defect that may delay a launch. When the yellow report was presented in the meeting, a deathly silence ensued. What's going to happen? Usually green. There's one yellow now. So what did Mulally do? Well, he responded with an applause. And that made the dreadful feeling lifted off the senior executives, I don't know, whatever they have. And then they thought, okay, actually, it's okay to share cautions and problems. It's even celebrated. And afterwards, the weekly staff meetings were full of colors. In the case of Ford Motor Company, before Mulally's arrival, communication was hard because the messengers, even the most senior executive, were reluctant to inform bad news to their bosses and colleagues. So this is when the senior executives and managers have what Claire said, the guilt, the shame, and despair. Let's just hide everything. Everything's okay. Don't look at my imperfection. Yeah, that's not going to work. Amy C. Edmondson is a professor of leadership and management in Harvard Business School. She studied many organizations for many decades. And she found that the behavior of the mid-level managers are very important in learning lessons from failures in organizations. And the behaviors include: how do they respond to failures? whether they encourage open discussions of failures. Do they welcome questions? Do they display humility and curiosity? In the case of NASA accidents, the messengers were ignored. In the case of Ford Motor Company, the messengers did not want to speak up, flag problems, or admit mistakes. Amy Edmondson said that the remedy is to reduce the stigma of failure. But how do we reduce the stigma of failures in software engineering? Naturally, when we develop software, we learn by failing, right? With TDD, we create failed tests, and then we make it green, and then refactor. But outside of coding, we still learn other lessons. We still make failures and mistakes. So, if we think of the software project level, what if we start recording the lessons learned for each software project and actually make it part of the success metrics of the project? Make it a KPI. So every software project must have a list of lessons learned. Don't hide them. Don't hide the failures. Just open up and then tell us what you learned from the mistakes for this project. Now let's look at another part of software engineering world. Performance review, either annual review or however often you do review, either with your managers or with your direct reports, only if you do performance review. Maybe you do performance review with yourself, I don't know. But when we do that, do we usually bring up the lessons learned, or do we only talk about all the successes? I don't have direct reports. With my manager, I usually say, hey, look at all of my achievements. I'm not going to talk about all of my mistakes and failures here. That's not going to help with my career and salary. But actually, what if we encourage it? What if we add learning and adaptations in the performance review? Because that's just the nature of software engineering, right? We make a lot of mistakes, just like what Dave Farley said in his keynote. We make a lot of mistakes so that we can achieve the goal. If you don't do mistakes, it's going to be very hard to achieve the goal. Even early on, when we write our resumes or curriculum vitaes, or reading candidates' curriculum vitaes, do we see any failures or hardships in there? Maybe we can encourage it. Put it in the job description. Say, when you write your resumes or CV, put them in. We want to know how you handle them, because it's a very important skill in software engineering. So all of these are to build the psychological safety in teams and organizations. Psychological safety is the belief that one will not be punished or humiliated for speaking up with ideas, questions, concerns, or mistakes. In teams, it refers to team members believing that they can take risks without being shamed by other team members. In safe and compassionate teams and organizations, failures can be found and brought up early. And we do need to detect failures before we can do the next activity, which is to analyze them. Failure analysis is the part where we reflect on the failures to gain and learn the lessons. Professor Edmondson advised that the job of leaders is to see that their organizations don't just move on after failure, but to stop and dig in and discover the wisdom contained in it. What does failure analysis look like in software engineering? Well, some of them can show up as code comments, for example, or commit messages, or bug reports. Some of them can be written as internal articles, playbook, web pages. Some of them can be in workplace conversations, in the messaging tools, or in recorded meetings in the transcripts. Some of them can show up as project or team retrospectives. Some of them manifest as incident or post-mortem reports. I'll call all of these recorded failure analysis as lessons learned logs. They are collections of recorded failures and the analysis done on them. Now, code comments can be very different from workplace conversations, or project retros, or post-mortem reports. However, although the media and content of the logs are very different, there are key parts that make them valuable as lessons learned logs. What are these parts? Okay, let me start with an example. Say, if you find a code comment that says, from June 2023, which is next month, we should run our batch job twice a day. Do you think it's a lesson learned log item? Well, it's not, because it's missing something. The facts. Lessons learned log must state the facts. It includes the description, also numbers, or diagrams, or other details that can help the readers to understand the background behind the lesson. Without the facts, we lose the why behind the ideas, or recommendations, or proposals that will come later on. Okay, another example. Say, if you find a retro documentation that says, based on our exploration and experimentation on the current state of mobile app development, we recommend to serve HTML payload from the server. What's missing here? What do they mean by the current state of mobile app development? What's missing is the time. Without the time, the readers will lose context on what else were happening when the lesson was learned. In the previous example, we could find out what the log meant by current state of mobile development if we know when the exploration was made. Was it made this year? 5 years ago? 10 years ago? It will be very different. Okay, another example. Say you found a post-mortem report that says, on 26th of May 2023, which is today, 90% of users experienced a degraded performance. It lasted for 30 minutes. This was caused by a bug that tried to read 50 years worth of cached data. Is this a lesson learned log item? No, because it means the idea, or recommendations, or proposal, however you want to name them. Without this part, the writer will lose the reflection part, and therefore can risk not learning the lessons. And without this part, the readers will not be sure of the lessons, and they don't really know what the next steps are. Well, yes, the readers can create their own ideas, but it's still essential for the writers to analyze the failure and come up with ideas in the first place, because they have the most context when they write the log. These key parts are needed for the benefits of both the log writers and the readers. Well, most importantly, the readers, because the logs are ideally written once and read many, many times by many, many people. Apart from having the key parts, the lessons learned is also ideally logged regularly. For example, every week. You could book a regular event on your calendar to look back on what lessons you have learned in the past week. It could be a team activity to do together. Well, so far, the good news is that most of us have probably been writing lessons learned logs without us even realizing it. Logging lessons learned log is not the goal, though. By itself, it's not going to improve software development that much. So what do we do with the logs? Before talking about what we do with them, let's look back at some ways we can log them. That's okay. Some of us may have been logging or thinking about starting to log lessons learned. So it can show up as a failure reports, postmortem, or incident reports, or project retros. It can come up as articles or blog posts. It can show up as code commits or pull request descriptions. It can also be inside workplace conversations. However, not all of these are lessons learned logs. Only those that contain the main elements, the fact, the time, and the ideas, can be highly valuable and considered lessons learned logs. The goal of logging the lessons is to seek the wisdom out of them whenever we need it. The lessons learned are not necessarily our own experience. It could be from other people. Well, ideally, most of the time, it should be from other people, because that's how we benefit the most from the collective knowledge of the lessons learned. And with the vast array of technology that we have now, currently, and the pace of the advancement of technology, we just can't know everything. We have to learn from each other. So we have to share our mistakes and our lessons learned. So how do we seek the wisdom out of the lessons learned logs? For failure reports or articles or blog posts, we can use the search functionality that comes with the content management system or the knowledge management system. If it's on the internet, we can use web search. For code commits and pull requests, we can use code search functionality in our own IDE or on the repo. These are just some examples. It's not an exhaustive list of how lessons learned can be logged and fetched. What's important here is that we are able to access them whenever we need them. And we should be able to access the three key parts: the facts, the time, and the ideas. If they are not accessible, then they are not very beneficial for other people. If we cannot search them, like if they are recorded meetings without any transcripts, then we cannot really search them. It just stays there. Most of the lessons learned logging tools that we have been using provide keyword search functionality, where we search by specific words and it responds with logs containing those words. Some of the tools may even provide semantic search functionality, which is to search by meaning instead of an exact word match methodology. With the pace of the AI technology, I'm pretty sure many of these tools will soon allow searching by meaning too. Otherwise, if the tools do not provide searching by meaning functionality, maybe we can build it ourselves, feed the lessons learned logs into and train a large language model, LLM, yes. And then we can query it. We can query that model. Imagine a time, probably in the near future, when you are about to start a project and you research possible solutions and potential pitfalls. And you ask with plain language, maybe by typing, maybe by talking, I don't know, let's see what's in the future. And you ask the lessons learned system. Say, for example, you say, we're building a product where users can sell handmade wooden arts. What would be the benefits and drawbacks of building a web app versus a mobile app for it? And then the system may respond saying, these are the recommended tech stacks, and based on the previous projects, these are the number of people and time you need to build similar projects. And these are the degree of previous user adoptions on web versus mobile apps and the breakdown of their demographics. But the response should also tell you the time of the lessons learned, so you can decide whether it still applies for your current one. From the space shuttle accidents and the Ford Motor Company's low performance, we learned that failures in communications leads to failures to learn. The symptom shows us messengers' voices being ignored, or the messengers chose not to speak up. The remedy is to increase compassion, to create and maintain psychological safety. A healthy and innovative team or organization should have a steady stream of new lessons learned logs. Every week, ask yourself, what have I learned this week? What have we learned this week? And don't forget to write down the key parts, the facts, the time, and the ideas. If you keep logging the lessons learned every week, then it's great. But if you find it hard to log the lessons learned, check if there's any psychological safety issue and fix them. Thank you very much. Do we have time for question? Okay, one question? Okay, cool, yeah. Any questions? Yes? Yeah, okay, so the question is, in a multicultural team, how do we deal with some cultures that are more comfortable with opening up and owning mistakes compared to cultures that are more, I wouldn't say hiding the truth, more shy. They are more shy. And I am from a culture where we are more shy. And what I learned for myself is that at workplace, when I open up about my mistake, it shouldn't be an attack for myself. And it should be about advancing the team to help with the decision making, to make the team more innovative. So thinking about the team and don't think about me too much. And it really helps if the team is passionate, not passionate, compassionate. And so I've been in teams where there was not much psychological safety, and me coming from a shy culture, found myself not saying anything. And usually people gave me feedback, why are you so quiet, Dee? If you have something to say, say it. I mean, yeah, it's easy for you to say, but I don't feel safe. And I didn't even feel safe to say that I wasn't safe. So try to pick up the symptoms. If some people are quiet in some meetings, but they actually talk somewhere else, somehow, I don't know, in code commits, they suddenly put a lot of very useful things in there. So maybe there's some psychological safety issue there to be fixed. I don't know if that helps. Cool, thank you very much. Any other questions? Okay, and that's my Twitter handle and Mastodon handle, so if you have any other questions, suggestions, ideas, feel free to just hit me there. Thanks very much, everyone.